Ohm's law. Picture a young Georg Simon Ohm in 1827, hunched over copper wire in a Cologne classroom, measuring something nobody had cleanly defined yet. He discovered that voltage, current, and resistance are locked in a permanent triangle. Voltage equals current multiplied by resistance. That's it. 3 variables, 1 equation, and every circuit ever built bows to it. The shocking part is how long engineers fought this idea. The French Academy of Sciences dismissed his paper as too simple. Too simple. But simplicity was the whole point. Every time a phone charges, a motor spins, or a light turns on, Ohm's triangle is doing the bookkeeping. Change one variable and the other two feel it instantly. Resistance doubles, current halves. Voltage drops, current drops with it. The law doesn't negotiate. It doesn't have exceptions. It is the grammar of every electrical system on the planet, and it was almost buried by academic pride. Voltage. Stand next to a high-voltage transmission line and you feel it before you touch it. A faint buzz in the air, hair rising on your arms. Voltage is electrical pressure, the force that pushes electrons through a conductor. The analogy that actually works is water pressure in a pipe. High pressure means more force pushing the water through. High voltage means more force pushing electrons through the wire. The unit is the volt, named after Alessandro Volta, who built the first true battery in 1800. A standard AA battery produces 1.5 volts. A household wall outlet in the US delivers 120 volts. A transmission line running across the countryside carries 345,000 volts or more. Here's the pivot. High voltage isn't automatically dangerous. What kills is current, not voltage alone. But high voltage makes high current far easier to produce. The combination is what engineers spend their entire careers managing. Every transformer, every insulator, every safety rating on every piece of equipment is a negotiation between voltage and the damage it can enable. Current. Think of electrons as a crowd moving through a hallway. Current is how many of them pass a single point every second. The unit is the ampere, named after André-Marie Ampère, who mapped the relationship between current and magnetic fields in the 1820s. 1 ampere means roughly 6.24 quintillion electrons flowing past a point per second. That number is almost impossible to picture. But here's what makes it concrete. A 60-watt light bulb draws about 0.5 amperes at 120 volts. A toaster pulls around 8 to 10 amperes. A car starter motor can demand 200 amperes for a fraction of a second. The dangerous threshold for the human body is somewhere around 0.1 amperes through the chest. That's 1/10 of an amp, less than what a nightlight draws. The cost of misunderstanding current is measured in electrocution statistics. The pivot here is that current doesn't care about your intentions. It flows wherever resistance is lowest, and if that path happens to be through you, it will take it without hesitation. Resistance. Every material pushes back against electron flow to some degree. Resistance is that pushback, measured in ohms. Copper has very low resistance, which is why it's inside almost every wire you've ever seen. Rubber has extremely high resistance, which is why it wraps around those wires. The relationship is not just about material. Length matters. A longer wire has more resistance than a shorter one made of the same material. Thickness matters too. A thicker wire has less resistance because more electrons can move through it at once. This is why extension cords have ratings. Run too much current through a thin, long cord, and resistance converts that electrical energy into heat. That heat has nowhere to go. The wire gets hot, the insulation melts. The fire starts. The US Fire Administration has linked thousands of residential fires per year to misused extension cords and overloaded circuits. Resistance isn't a flaw in the system, it's a fundamental property. The flaw is pretending it isn't there. Circuits. Imagine a loop. Electricity needs a complete, unbroken path to flow, and that path is a circuit. Break the loop anywhere and current stops. This is why a light switch works. It physically interrupts the circuit. Close the switch, complete the loop, the light turns on. Open it, break the loop, the light goes off. There are two fundamental arrangements. Series circuits connect components end to end like beads on a single string. If one bead breaks, the whole string fails. Early Christmas tree lights were wired in series, which is why one burned-out bulb killed the entire strand and drove generations of families to quiet madness every December. Parallel circuits connect components side by side, each with its own path to the power source. One path fails and the others keep running. Your home is wired in parallel. That's why unplugging the lamp doesn't turn off the refrigerator. The pivot is that neither arrangement is universally better. Series circuits are simpler and cheaper. Parallel circuits are more reliable. Real systems use both, layered together, and the engineer's job is knowing which combination fits the stakes, power. In 1882, Thomas Edison threw a switch in Lower Manhattan and lit up 1 square mile of the city. He was demonstrating electrical power, the rate at which energy is delivered or consumed. Power is measured in watts, named after James Watt. The formula is elegant. Power equals voltage multiplied by current. A 100-watt bulb running at 120 volts draws about 0.83 amperes. Scale that up to a city and the numbers become staggering. The average American home consumes roughly 10,500 kilowatt-hours of electricity per year. A kilowatt-hour is 1 kilowatt of power running for 1 hour. Your electricity bill is just a count of those hours. Here's where it gets interesting. Edison's system used direct current, DC, which loses power rapidly over long distances due to resistance. His rival, Nikola Tesla, backed alternating current, AC, which could be stepped up to high voltage for transmission and then stepped back down at the destination. AC won. The war of currents ended with Tesla's system powering the modern world, and Edison's reputation in electrical history took a hit it never fully recovered from. Alternating current and direct current. A battery produces DC. The electrons flow in one direction, steady and constant. Plug your phone into a wall outlet and something different is happening. The current is alternating, reversing direction 60 times per second in the US and 50 times per second in most of Europe. That reversal is AC. The reason AC won the infrastructure war comes down to transformers. A transformer can only step voltage up or down with AC. You can't transform DC with a simple coil. High voltage means lower current for the same power, and lower current means less energy lost to resistance over long transmission lines. So AC travels across continents efficiently, then gets stepped down to safe levels at local substations. DC is making a comeback. High-voltage direct current transmission lines are now used for very long distances because modern power electronics can convert and control DC in ways that weren't possible in Edison's time. The pivot is that the current war never really ended. It just moved into a new phase, and both sides are winning different battles. Capacitors. Drop a capacitor into a circuit and it does something counterintuitive. It stores electrical energy in an electric field between 2 conductive plates, separated by an insulator. It charges up fast and releases that charge fast. Not slowly, like a battery. Instantly. A camera flash uses a capacitor for exactly this reason. The battery is too slow to deliver the burst of energy needed for the flash. The capacitor charges over a second or two and then dumps everything in a fraction of a millisecond. That's the design. The daily mechanics are everywhere. Capacitors filter noise from power supplies. They smooth out voltage spikes. They time the oscillations in clocks and radios. In power factor correction systems, they compensate for the inefficiencies created by motors and transformers. The cost of getting them wrong is real. A capacitor rated for 50 volts connected to a 100-volt source will fail catastrophically, sometimes violently. The pivot is that capacitors also hold a charge after power is removed. Open the wrong piece of equipment without discharging the capacitors first, and the energy stored is still there, waiting. Technicians have been seriously injured by capacitors in equipment that had been unplugged for hours. Inductors. Where a capacitor stores energy in an electric field, an inductor stores it in a magnetic field. Wind a wire into a coil and run current through it. A magnetic field builds around the coil. Stop the current and the field collapses, pushing that stored energy back into the circuit as a voltage spike. This is called back EMF, and it is one of the most misunderstood hazards in electrical engineering. Disconnect an inductive load like a motor or a relay coil too abruptly, and the back EMF spike can be many times higher than the supply voltage. That spike destroys transistors, burns out microcontrollers, and corrupts data in digital systems. Engineers use flyback diodes across inductive loads specifically to absorb these spikes. Without that single diode, a motor control circuit can destroy itself the first time it shuts off. The pivot is that inductors are also the heart of every transformer, every radio antenna, and every switching power supply. The same property that makes them dangerous makes them indispensable. The magnetic field they create is the mechanism that transfers energy wirelessly between coils, which is the entire operating principle of wireless charging technology used in billions of devices today. Semiconductors. In 1947, 3 physicists at Bell Labs in New Jersey built something the size of a human palm that would eventually shrink to fit billions of copies on a fingernail: the transistor. The key was the semiconductor, a material like silicon that conducts electricity under some conditions and blocks it under others. That switchable behavior is the foundation of every digital device ever made. A transistor acts as a gate. Apply a small voltage to the control terminal and it opens, allowing current to flow. Remove that voltage and it closes. On and off. 1 and 0. Binary logic made physical. The pivot is scale. In 1965, Gordon Moore observed that the number of transistors on a chip was doubling roughly every 2 years. That observation, Moore's law, held for decades. A modern processor contains over 100 billion transistors, each one switching billions of times per second. The enemy pressure on Moore's law is physics itself. Transistors are now measured in nanometers. A few nanometers is approaching the size of individual atoms. Quantum effects start to interfere. Electrons tunnel through barriers they shouldn't be able to cross. The semiconductor industry is now fighting the laws of physics directly, and the outcome is genuinely uncertain. Electromagnetic induction. In 1831, Michael Faraday moved a magnet through a coil of wire and watched a current appear in the wire from nowhere. No battery, no connection to any power source. Just motion and magnetism producing electricity. This is electromagnetic induction, and it is how virtually all electricity on the planet is generated. Coal plants, nuclear plants, wind turbines, hydroelectric dams, they all spin a coil of wire inside a magnetic field. The details differ. The fuel source differs, but the fundamental act is the same one Faraday performed with a magnet and a coil in a London laboratory. The pivot is that induction works in reverse too. Run current through a coil near another coil and you induce a current in the second coil without touching it. That's a transformer. That's wireless charging. That's the induction cooktop that heats your pan without a flame. Faraday had no formal mathematical training. He described his discoveries in physical, intuitive terms. James Clerk Maxwell later translated Faraday's ideas into the mathematical equations that became the foundation of classical electromagnetism. Two men, two completely different minds, one unified theory that still governs every antenna, every motor, and every generator on Earth. Grounding and safety. In 1972, the US National Electrical Code made 3-prong outlets mandatory in new residential construction. That third prong, the round one at the bottom, is the ground. It connects the metal chassis of appliances directly to the earth. Under normal conditions, no current flows through it at all. It just sits there, but if a wire inside the appliance breaks and touches the metal case, the ground wire gives that fault current a safe path to flow. It trips the breaker, the appliance shuts off. Without grounding, the metal case sits at a dangerous voltage and the next person who touches it completes the circuit through their body. The pivot is that grounding is not just about shock prevention. It stabilizes voltage references in sensitive electronics. It suppresses electromagnetic interference. It is the reason your audio equipment doesn't hum constantly. Ground loops, where two pieces of equipment have slightly different ground potentials, can inject noise into audio and measurement systems that is genuinely maddening to diagnose. Engineers have spent weeks tracking down a 60-cycle hum that turned out to be two pieces of equipment plugged into outlets on different circuits. Safety and signal integrity are the same problem wearing different clothes. Electrical engineering is not a collection of separate ideas. It is one idea, repeated at every scale. Energy moves, something resists it, something stores it, something converts it. The engineer's entire job is managing those 4 verbs across every voltage level, every frequency, and every material on the planet. The rules don't change. Ohm's law holds in a microchip and in a transcontinental power line. Faraday's induction principle runs a wind turbine and charges a toothbrush. The basics are not the beginning of the story. They are the whole story, just expressed at different magnitudes. Learn them once and you can read every circuit ever drawn.